Today I'll be talking about the White Hill Formation in the Karoo Basin in South Africa. And the reason why this layer is of importance is it's currently the focus of shale gas exploration. And previously several boreholes have been used to study this layer, but we now are looking at some old seismic data that was never published along with these boreholes to create depth maps of the basin. And we're using these new depth maps to look at flexure modeling of this layer to better understand how the basin formed, because there's several theories of formation. And the basin location itself, you can see this red line, it covers most of South Africa, and it stretches from on Craton in the northeast to off Craton on the surrounding mobile belts in the southwest and southeast. And in the southern part of South Africa, there is the Cape Fold Belt, and it is the loading of this belt on the crust at the time of formation of the Karoo Basin that is thought to have led to basin formation. And so we're going to be looking at that today with our flexure modeling. In terms of what data has been used, like I've mentioned, we've got seismic and borehole data that have given us depth profiles, and you can see in the image here we have a depth to the top of the White Hill. The boreholes are shown as triangles, white and black, and the black lines in the south are the seismic lines. And so what we're going to do is we're going to take these three profiles that are marked, the red lines, P1, 2, and 3, look at the depth profiles along them and compare them to several flexure models using Flex 2D software, and then use these to determine what the strength of the crust at formation and the load, height and width. So this Cape Fold Belt in the south, how big was it that actually led to the bending of the crust? So we're going to be looking at these two parameters. When we do flexure modeling, you can see here, we assume that the lithosphere is an infinite elastic beam with a strength TE. And in this image, the horizontal line that is bending down is the lithosphere, and the gray square is the load on the crust, and it's causing this bending. And the height of the load and the width of the load will affect the depth at which this elastic beam is bending. And then the strength of the crust will affect the wavelength of this bending beam. You can see a stronger crust doesn't bend as much, and a weaker crust bends significantly. So our model is going to look like that, but cut in half, because we have the Cape Fold Belt in the south, and then we're looking at bending to the north of it. So looking at our two profiles that we have here, here's profile 1 at the top, profile 2 at the bottom, and so we're moving from west to east. For profile 1, you can see the load on the left-hand side, and we've got several different models. And so that is the red, blue and green line, and we are fitting it to the dark black line, which is the depth profile. And so you can see the best fit model here is for an H or height of 4 kilometers and a TE or strength of 50 kilometers. And moving to the bottom here, I've plotted profile 1 and profile 2, so you can see how much the basin deepens towards the southeast. Profile 2, it's also got a red, blue and green line fitted to it, and the best fitting line is the blue model, which is a height of 8 kilometers and an elastic thickness of 85. And so this just highlights, as we move from west to east, the basin gets deeper and the wavelength of the depth profile is broader, and therefore we actually can only model it with a smaller height in the west, a height of 4 kilometers, and it increases to 8 kilometers in the east. This is of the load from the Cape Fold Belt, and then the strength of the crust is increasing from about 50 kilometers to over 85 kilometers in the east. If we look at a third profile, and this is in the far southeast of the country, our model starts to break down here. You can see I don't actually have a dark black depth profile because there was no seismic data shot, and so I've only got borehole data. And so the gray dots is the White Hill Formation, and the red dots is the base of the Karoo Basin. And you can see the White Hill is just in the southern part of this profile, doesn't extend on Craton. You still need a model with an extremely high elastic thickness to be able to fit the depths in borehole SP and borehole WE. And you can see the models there in red and in blue have an elastic thickness of 100 kilometers or above. And maybe the elastic thickness was too large for the White Hill to be deposited on Craton. So in conclusion, We really see that the large extent and shape of the Karoo Basin could be due to flexure. Many people have argued that the basin is too large for that to be the only mechanism. We've seen that the whitetail deepens to the southeast, and we've shown that this could be due to an increase in load height. And in linking this to tectonic scenario, it could be due to locking on the subduction zone further south that is actually forming this Cape Fold belt. We've also shown that this deepening in the basin is due to an increase in elastic thickness of the lithosphere. We actually linked this to asthenospheric buoyancy anomaly. And so you'll notice in this image here that the topography is plotted. So a large part of South Africa is at very high elevations. And this has been suggested to be due to buoyancy anomaly. On the eastern side of the basin, a larger part of the anomaly underlies the basin. The anomaly is at great depths, at 150 to 190 kilometers, so it's making the crust buoyant rather than heating up the crust and breaking it down. And this could be linked to the larger elastic thickness.